Well, that brings us to the periodic table. Now, it is now possible for us to take all the elements and put it together in a table so that we can study the characteristics. Now, the periodic table of elements is organized like a big grid, so that all the elements with their symbols are given in that big grid. Elements are placed in rows and columns. Now, look at the way the periodic table, I haven't written down the names of the elements. Now, the periodic table has columns, look at the columns there, and rows. And each of these blocks is where you write the name of the element. The rows are called periods, and the columns are called group. So, if you take a column of elements, this is called a group of elements. Now, they all have something in common. Whereas, if you take a row of elements, it is called a period. Now, you got to remember those. The rows in a periodic table are called periods, and the columns are called groups. All the elements in a period, all the elements in a given period have the same number of atomic shells. In other words, if you take 1s, you see hydrogen, helium, that's the first period, and both has just one shell, S shell, and you can see 2s, 2p. You see, all these elements have the same number of atomic shells. That is the characteristics of elements in a period. All the elements in a period have the same number of atomic shells. Now, every element in the top row, that is the first period, has one orbital for its electron. 1s, 1s. Now, hydrogen, this is hydrogen actually. Hydrogen has one electron, that will be 1s1. Helium has two electrons, that will be 1s2. Both that electrons will be in the s subshell. Elements in the second row, the second period, have two subshells. That means all the elements here will have the S shell and the P shell. And those shells get gradually filled in. A column in a periodic table is called a group. We already talked about that. Now, the elements in the group have the same number of electrons in the outer shell. You see, as we go on filling the electrons, every atom has an outer shell. What is the characteristics of elements in a group? All the elements in a group, very interesting, watch this. All the elements in a group has the same number of electrons in the outermost shell, and that makes them all behave similarly in chemical reactions. The chemical properties of elements in a group are all the same because they all have the same number of electrons in the outer shell. Every element in the first column, that is group 1, has one electron in the outer shell. If you look at every element, that will be, those electrons in the first group will be hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. All these elements have just one electron in the outer shell. All other electrons are in other shells inside. The outer shell has just one electron. That is the characteristic there. Now, we will use dots to represent the number of electrons in the outer shell. Now, you see, the number of electrons in the outer shell is a very important chemical characteristic of elements. So we're going to concentrate on that. We will write the symbol of the element and use dots to represent the number of electrons in the outer shell. Now look at this, hydrogen with one dot. Well, hydrogen has only one electron anyway, and that is the S shell. Alright? Helium has 2 electrons in the outer shell. Lithium has 1 electron in the outer shell. Sodium, now I'm going to read the names, although I'm giving you the symbols. It's not required that you learn these symbols. So here, hydrogen, lithium, sodium, just 1 electron in the outer shell. Potassium has 1 electron in the outer shell. Rubidium has 1 electron in the outer shell. Cesium has 1 electron in the outer shell. Francium has 1 electron in the outer shell. Look at this. All these elements of group 1, they're called group 1 elements. They all have one thing in common. They all have 1 electron in the outer shell. But don't misunderstand me. They have a lot more electrons. They are all in the inner shells. But the outermost shell, all of them has only 1 electron. And that makes them chemically similar. Alright? Look at the second group. Beryllium has 2 electrons in the outer shell. Magnesium has 2 electrons in the outer shell. Calcium has 2 electrons in the outer shell. Strontium has 2 electrons in the outer shell. Barium has 2 electrons in the outer shell. And radium has 2 electrons in the outer shell. All elements in group 2 has how many electrons? 2 electrons in the outer shell. Alright? Let's now look at some elements in this period. Now, boron. How many electrons in the outer shell? 3 electrons in the outer shell. Anybody tell me what is going to be the next one coming? Carbon. Carbon has 4 electrons in the outer shell. Now, do you remember how many electrons carbon has? Carbon has actually 6 electrons. 2 of them are in the inner S subshell and 4 of them in the outer shell. So the outer shell, carbon has 4 electrons. Next element is nitrogen, and nitrogen has 2, 4, 5 electrons in the outer shell. Now the dots haven't come up very clearly. You look carefully, there are 5 dots there. Now oxygen has 2, 4, 6 electrons in the outer shell, and fluorine has 7 electrons in the outer shell. Now look as you go in a period. The row, elements in a row is called a period. Now as you go in a period, is there some predictability there? Well, 1 electron in the outer shell, 2 electrons in the outer shell, 3 electrons in the outer shell, 4 electrons in the outer shell, and so on. What do you think will be the number of electrons in the outer shell for this neon? Neon has 8 electrons in the outer shell. Well, now look at the way the periodic table is taking shape, the way the elements are organized. There is a specific rule used for organizing the elements. All the elements in a column, a group of elements, has the same number of electrons in the outer shell. But if you notice, there is a small exception for that for the last column. The first element is helium. It has only 2 electrons in the outer shell. But all others in here are going to have 8 electrons. Now fill in the outer electron configuration of elements in the group containing fluorine. Now, if you draw this group, how many electrons each of these elements will have? Now what you should do is, you should look in a periodic table, either in a textbook or go to Google and Google periodic table. It will give you any number of choice for you, and look for the symbols of the elements. Actually, they are fluorine, chlorine, bromine, iodine, astatine. So fluorine, chlorine, bromine, iodine. I'm going to write them down for you. Fluorine, chlorine, bromine, iodine, astatine. Well, that's enough. You go up to there. Fluorine, chlorine, bromine, iodine, astatine. Now fill in this column and write down the electron in the outer shell for each. Well, it's not much of a deal because each of them has 7 electrons in the outer shell. Okay. Now, groups are named using Roman numerals as shown below. So, the first group is called 1A, Roman numeral. Second group is called 2A, 3A, 4A, 5A, 6A, 7A, 8A. Well, the reason why these are all called 1A, 2A, 3A, because the periodic table has got 3 big chunks, 3 segments. A group, B group, and C group. So all these are the A group. That's why they're called 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Now remember, I haven't completed these. 3A has many more elements coming down. So each of these has many more elements. Alright. With the exception of helium, all the elements in the last group have 8 electrons in the outer shell. And that is a very important property. Now, with the exception of hydrogen, look at the first group. With the exception of hydrogen, all the elements in the first group are shiny, low-density metals, and you can actually cut them with a knife. If you take a sodium, for example, sodium can be cut like a piece of cheese. But please don't do that. Well, you cannot buy sodium from open market anyway. It's very dangerous. If you cut a piece of sodium and put it in water, it will violently react. There will be a violent reaction, an explosion. If you put a big chunk of sodium, there will be a big explosion. Because sodium reacts violently with water. In fact, all these will violently react with water. Now, these are called metals, and these metals are called alkali metals. So what are alkali metals? Alkali metals are metals in the first group. That doesn't include hydrogen. So starting from lithium, sodium, potassium, rubidium, cesium, francium, they all put together are called alkali metals because they react violently with water to form alkaline solutions. And also they release hydrogen in the process. Elements in the second column are called alkaline earth metals. Beryllium, magnesium, calcium, strontium, barium, radium. They are called alkaline earth metals, and they are soft reactive metals, but not as soft or as reactive as the first group of elements. The first group of elements are the most reactive of all these elements on the left side. Now, elements in group 7A, look at that: fluorine, chlorine, bromine, iodine, astatine. All have outside configuration of 7 electrons, and they need only one more to make 8 electrons. Now, let me talk about that. You see, when an atom has 8 electrons in the outer shell, it is said to be a properly completed outer orbit. Now, this is what every element wants to achieve. You see, the 8 electron configuration in the outer orbit is a very stable configuration. That means if an element has the 8 electron configuration in the outer orbit, it's a very stable element. In other words, it will not want to react with any other elements. Now look at these elements that I talked about, the last group 8A. Well, they will be neon, argon, krypton, xenon and radon. I will name them as we go on. All those elements, with the exception of helium, all these elements have 8 electrons in the outer shell. I want you to listen this carefully. We are going to use this in our next lesson. You see, when you have an 8 electron configuration, the element is very stable. It will not then want to react with any other element. That means these elements that have the 8 electron configuration does not want to react with any other element. Therefore, all these elements in here are very, very inert. What is the meaning of inert? Non-reactive. They don't want to mix with other elements. And for that reason, scientists call them noble elements. Why do we call them noble elements? If you know, British royalty or many other European countries' royalty, you call a nobleman if you belong to the royalty and you don't mix with the common people. So the common people, yep, you don't belong to me, I don't mix with you, right? I'm noble. In the same way, these elements do not want to react with any other elements. They are chemically inert. They are happy on their own because they have that stable 8 electron configuration, and for that reason they are called noble elements. You see, the tendency of every chemical reaction is to produce this 8 electron configuration so that you got stable products. So these elements, fluorine, chlorine, bromine, iodine and astatine, they have how many electrons in the outer orbit? 7. They need one more to complete that nobility, to complete that stability. Is that right? That means these elements are chemically very active. They are looking for an extra electron. Wherever they can grab an extra electron, they will grab. You see? That means if you bring sodium and chlorine together, you see, the chlorine will beg to sodium. Now look, sodium, you have just one lone electron in the outer shell. and I am longing for one more electron in my outer shell so that I can achieve nobility. Well, would you give me your electron? And sodium will be more than happy to oblige. Sodium will donate that extra electron. You know, while doing it, sodium becomes stable. And by taking that extra electron into here, chlorine gets 8 electrons in the outer shell. That becomes happy. And you know, from that day on, sodium and chlorine will stay together. And that is what we call sodium chloride, our salt. Our salt is a marriage between these two elements, sodium and chlorine, so that each will enjoy the nobility status of having 8 electrons in their outer orbit. You see, chemical reactions happen like this. So, what is these elements called inert? So, elements in group 7A have an outside configuration of 7 electrons, needing only one more electron to completely fill the outer orbit. Now, these elements are called halogens. So, what is the name for this group of elements? This group of elements is called halogens. Fluorine and chlorine are greenish colored gases. Now, most of you who buy chlorine for your pool, you know that. Chlorine can be dissolved in water. It sort of produces a yellowish liquid. Whereas bromine is a reddish liquid and iodine is a dark purple solid. In the olden days, this iodine dissolved in water used to be used for treating wounds. It's a sort of an antiseptic. Now, halogens react with metals forming salts. You see, these halogens, they need just one more electron to complete their outer orbit to make it 8. Remember, every element is dreaming for that, to get their outer orbit filled with 8 electrons. And the halogens need only one more electron. And the candidates to go for borrowing or begging for that one electron are actually these metals. You see? So, these halogens and these metals will react very well. By doing what? They will happily give off their lone outer shell electron, and these will happily take them, so that each is happy and they will live together forever. Is that right? Well, what will happen? Forming salts. So halogens combining with what? Alkali metals. These are alkali metals. So halogens chemically combining with alkali metals produces all kinds of salts. You can have sodium chloride, sodium bromide, potassium iodide, and so on. They're all different kinds of salts. Okay. Elements in group 8A have their outer orbits filled to capacity. We talked about that. Now here, neon, argon, krypton, xenon, and radon, all of them have 8 electrons in their outer orbit. The exception is helium. Now helium is happy because it has 2 electrons in the outer S shell. It's happy. It is also inert and noble. And all these gases are therefore called inert. These elements are colorless, odorless gases that almost never react with other elements. Why? They are not interested. They look at other elements as heathens. because these ones are happy. We've got all the complements of outer shell electrons. We are happy. We don't want to mix with you. So they never react with other elements forming compounds. So they are called inert. Sometimes they are called noble gases because they are chemically inert. They are not chemically active. The outer orbital electrons are mostly responsible for all the chemical properties of elements. Now, with this discussion, you should know that all the chemical action happens between elements. Now, mostly it is due to the number of electrons in the outer shell. So the chemical behavior of an electron is actually dictated by the number of electrons in the outer shell. And that's the reason why we have a particular system for representing the outer electrons. Actually, the electrons in the outermost shell of an element are called valence electrons. Valence electrons. Now, for hydrogen, there is one valence electron. Beryllium, there are two valence electrons. Carbon, there are 4 valence electrons. Fluorine, there are 7 valence electrons, and so on. So elements in a group have the same number of electrons in the outer shell, and therefore they are all chemically similar. Elements that have the same number of valence electrons, the number of electrons in the outer shell, are chemically similar. Now, here I have given you a table with all the elements and their symbols. Now, the groups I'm talking about, A group, B group, C group, you don't need to worry much about it. The way that the table is structured also shows how to predict the electron orbitals. On the left is a block of 2 columns. Then on the right there is the block of 6 columns. You see, these 2 blocks put together is your A group. In the center is a block of 10 columns, and at the bottom we have a block of 14 columns. That makes up the entire periodic table. Alright, the valence shell. What is the valence shell? You see, the number of electrons in the outer orbits are called valence electrons. And so the valence shell is the outer shell. The valence shell or the outer shell, the shell with the highest energy level, is that right? As you go higher, outer and outer, the energy becomes higher and higher, is the one mainly responsible for how an element reacts with compounds. So the chemical reaction between elements are actually dictated by the number of valence electrons, the number of electrons in the outermost shell. The core electrons, electrons which are at the center, they are buried deep within the atom and usually do not take part in chemical reactions. They don't play an active role in chemical reactions. All chemical reactions are controlled by valence electrons. All right. Now, during chemical reactions, elements like to gain or lose electrons. What is the incentive for chemical reaction? The incentive for chemical reactions is to obtain the complete 8-electron structure. You see, every element wants to get that 8-electron outer valence shell structure. That is the incentive for chemical reaction. So, during chemical reaction, some elements will lose electrons, some others will gain electrons in order to achieve that 8 electrons or filled electron outer shell. Alright, now let's now talk about metals, non-metals and semiconductors. When an atom loses or gains electrons, it has an unbalanced electron charge and is called an ion. Well, you remember I told you sodium, how many electrons are there in its outer shell? 1 electron. And it will be very happy to lose it. If sodium loses that electron to some other element, now sodium now has 1 electron less or 1 negative charge less. That means sodium now has a net positive charge. You see, such an electrically charged atom is called an ion. So what is an ion? An ion is an atom that has a net positive charge. Now look at this. Sodium look like this. Alright, let me see if I can find that for you. How many electrons sodium has? Anybody know? Well, sodium has 11 electrons. And you know how they are represented. N equal to 1, there are 2 electrons. N equal to 2, there are 8 electrons. And a lone one is at N equal to 3. So the outer shell has 1 electron. If sodium can get rid of that, then it will have 8 electrons in the outer shell. So sodium is very happy to get rid of it. So let's take that away. If this electron now goes away, this is now got a net positive charge. Now we write it like this. Sodium now has a net positive charge because it lost 1 electron. It is now called a positive ion. So when an atom loses or gains electron, it has an unbalanced electron charge and is called an ion. Okay. Well, chemical reaction, these ions are very important. An atom of lithium has 3 protons and 3 electrons. It is electrically neutral. If it loses an electron, it becomes an ion with a net positive charge. Now, elements with 1, 2, or 3 outer electrons tend to lose electrons. For example, all these elements has 1 electron in the outer shell. All these electrons has 2 electrons in the outer shell. And these elements has 3 electrons in the outer shell. Now, are they happy? No. There are too few in the outer shell. They want to get rid of them. So, elements with 1, 2, or 3 outer electrons tend to get rid of them, tend to lose electrons and form positive ions. Now, such elements are called metals. Metals are elements that tend to lose electrons to form positive ions. And you can see the elements on the left side are all metals. They tend to lose electrons to become positive ions. Non-metals. Now, elements on the right side, particularly fluorine, chlorine, bromine, iodine, astatine, they are hungering for 1 more electron. You see that? They tend to gain electrons, becoming negative ions. They are called non-metals. Non-metals are elements with 5 to 7. You see, if you look here, from this group onwards, they have 5, 6, 7. This group has 5 electrons in the outer shell. This group has 6 electrons in the outer shell. And this group has 7 electrons in the outer shell. They want more. So they will be very much ready, willing to accept more electrons. And they are non-metals. Metals that tend to accept electrons are non-metals. Non-metals are elements with 5 or 7 electrons, 5 to 7 electrons in their outer shell, and they tend to acquire electrons to fill their outer shell. Elements located on the left 2/3 are all metals. Non-metals are on the right of the table. The line of separation is not quite clear, so you don't need to worry about it. Elements around the line of separation sometimes both act as metals and non-metals. You see, mostly the line of separation falls that way. But these metals are sort of in between, and they are sometimes called, semiconductors and so on. Well, do we have a complete picture of what the universe is now made of? Do we have a picture of the elementary particle? What is the basic building block of our universe? Now, do we have a good picture of the atom? The present day understanding of atomic structure is described by a theory known as the Standard Model of Particle Physics. Well, what we discussed so far, the quantum model, is one way of describing the Standard Model. Now, this describes the fundamental building blocks and the forces through which they interact. Now, there are 12 basic building blocks. According to the Standard Model of Physics, there are 12 basic building blocks. In other words, an atom can be broken down into these 12 basic building blocks. What are they? There are 6 quarks, and they are characterized as up quark, down quark, charmed quark, strange quark, bottom quark, top quark, and so on. Now, these are different kinds of quarks, and there are particles called leptons. There are 12 fundamental particles. There are 4 fundamental forces in the universe. Now, what are these fundamental forces in nature? What are the forces that hold the universe together? Well, the most prominent force in the universe is the force of gravity. When I drop something, well, if I drop my aluminum pointer, it's going to fall to the ground. Is that right? Yes, because of the force of gravity. Everything in the universe attracts everything else with a force we call force of gravity. In fact, stars will not form without gravity. Solar systems will not form without gravity. There will be no universe without gravity. So it is the force of gravity that makes it possible for all matter to come together and behave in the organized way that we are used to seeing it. So, that is the first force that holds the universe together. There are other forces, electromagnetic forces. Now, what are these electromagnetic forces? Now, let me see if I can illustrate to you what is called an electric force. Now, I have a little light ball suspended here, and I'm going to rub a plastic sheet with a little wool. and see what happens when I bring it close to the suspended light. Well, it's a very light ball. See what happens. There you are. Did you see what happened? Now, when I bring it closer, you see, well, I can make it dance. I'm not touching it. Look at the way I'm going to make it dance. Isn't it wonderful? This is one of the tremendous forces that is in the universe. This is the electric force. Now, why is this going away? Well, because this plastic sheet I'm holding and the metal ball has both the same type of electric charge. You see, it came and touched it. And now they have both the same type of charge, and now these charges are repelling each other. So there is electric force. How about magnetic force? Have you played with magnets? I'm sure you have played with magnets. Now, I have a magnet here, and let me see if I can show that to you. Well, here is a magnet. And if I keep a magnetic material, now look at my, well, aluminum rod is not going to be useful there. If I get a steel rod, let me see if I can find my steel rod. Now look at the way this magnet behaves when I bring this iron rod near it. Now look at that. I can now hold that magnet with the iron rod. You can see it's, if I want to separate it, hey, I got, you see, I got to use a tremendous amount of force. Now look at the magnetic force. Now here I have a very heavy iron, well, this is an iron stand. See what happens when I bring, can I lift this with my magnet? See what happens. Look at that. I can lift it with my magnet. The magnetic forces are so strong. So electromagnetic forces are a dominant force in the universe. Now, what other forces are there? There are other forces. They're called strong and weak forces. Now, we talked about the nucleus of an atom. Now, you know that protons are positively charged particles. You also know that like charges repel. I just showed you how the light ball was repelled away from the plastic sheet. They were similarly charged. So, what is the force that holds the positively charged protons together in that very small space, the core of the atom, the nucleus? Now, that force is called the strong force. There is some strong force that holds the nucleus of the atoms together. Can you imagine what happens if there is no strong forces available? If there are no strong forces available, then matter will not come together to form atoms. A nucleus cannot exist. That means the matter as we see now cannot exist. So the universe, the existence of the universe as we see, depends on all these forces. Gravitational force, electric and magnetic forces, strong forces that hold the nucleus together, and weak forces. Weak forces are the forces that help the nucleus to disintegrate. Now, we talked about that briefly, but in the next class we will talk about it more. Now, all these things put together is what holds the universe together. The universe will not exist without these fundamental forces. In fact, if you ask me to define universe, I would say the universe is defined by these four fundamental forces. What are the fundamental forces? Are the force of gravity, the force of electromagnetism, the force between electric charges, the force between magnets, electromagnetism, the strong forces that hold the nucleus together, and weak forces that sometimes tend to disintegrate the nucleus. All these forces put together is what constitute the universe. Now, the Standard Model described the behavior of all these particles and forces except gravity. Now, any model of the atom, if you have a satisfactory model of the atom, that model of the atom must explain the existence of all these forces. Now, if there are 4 forces that constitute the universe, then there must be a common origin for all these forces. Now, can you understand that? If these forces have different origin, then you cannot say that the universe originated, say, from a Big Bang. Now, if the universe originated from a Big Bang, all these forces also started at that time from the Big Bang. That means we should be able to trace all these forces back to some single entity. Or you must be able to unify all these forces into one model or one theory. Now, this is what the scientists are now striving for, looking for a unified theory which will explain all these 4 forces. Now, the Standard Model can do that, can unify electromagnetism, weak and strong forces, but when it comes to gravity, it behaves in an entirely different way. Now, Standard Model cannot unite all these 4 forces together. Now, as long as you cannot unite all these forces together, the model that we have is not a perfect model. Now, in the past few decades, another theory, a different theory altogether, has sprung up. And this theory is called the string theory. String theory has emerged as the most promising candidate that is likely to unite all these 4 forces and lead us into something that is unique and something that can be called a unified super theory of everything, the theory of everything. So it is a promising candidate for a microscopic theory of everything. It means it will satisfactorily explain the origin of gravitational, electromagnetic, weak and strong forces. Well, we will not spend a lot of time talking about it. String theory is still evolving. It is still a theory that is controversial because among the physicists there is a group who believe in it, there is a group that don't believe in it. So it's a controversial theory. Now, what does it attempt? String theory attempts to unify all existing theories about the universe. Now, according to the string theory, absolutely everything in the universe is made of, well, is comprised of very tiny vibrating particles. Now, I have shown you how a string, a stretched string, vibrates, producing nodes and antinodes. Is that right? Well, this is basically what the fundamental string does. So all of the particles that make up matter, you see, matter and forces, the 4 forces we talked about. According to string theory, all matter and all forces that hold the matter together are comprised of tiny, very tiny, it's so small that it is virtually impossible for any means to locate them, are made up of these tiny vibrating fundamental one-dimensional strings. Now look at this. This is a one-dimensional string. A string can be a closed string or an open string. Now look at the different modes of vibration. Do you remember when we talked about the vibrations of the string? A string can vibrate in its fundamental mode, in its second mode, third mode, fourth mode. In fact, these tiny vibrating strings, they are actually strings of energy. They can vibrate in different varying mode, and each fundamental particle that we have been talking about, electrons, protons, photons, all these particles are the different modes of vibrations of these fundamental strings. A particle is like a note played on a guitar. When you pluck a string on a guitar, it produces a musical note. Is that right? Well, because it sets the stretched string into a mode of vibration. In the same way, a particle is a resonant mode of vibration of the fundamental string. You can make the fundamental string vibrate in different modes. It will then represent different particles. Just the same way, you can produce different notes from the same stretched string on a guitar. So, a particle is like a note played on a guitar. The only difference between one string and another, whether it's a heavy particle that is part of an atom or massless particle that carries light, photons are assumed to be massless particles. So all these particles are different resonant patterns. Now I'm sure you are able to understand the meaning of resonant patterns. I showed you the different resonant patterns of the string. A string can resonate with its fundamental frequency, or twice the fundamental frequency, 3 times the fundamental frequency. Each of those resonant modes represent a fundamental particle. The vibrational pattern determines what kind of particle that string is. So it's the pattern of vibration that determines the kind of particle the string represents. So basically everything that is the universe is made of is fundamentally, it is those basic fundamental strings. The vibrations of those strings is basically responsible for everything that we see in the universe. Now, one resonant pattern makes it a photon, for example, while another makes it a heavy particle found within the nucleus. You see, normally if you look at the structure of these particles, a particle found in the nucleus, a proton, is a heavy particle that has a mass. A photon is simply a packet of energy. There is no mass. It's a massless particle. But both these particles are different modes of vibrations of the same fundamental string. You can see here, you can see the different modes of vibration. If one mode represents the massless particle photon, another mode of vibration can represent the heavy particle, the proton, neutron, electrons, and so on. Well, for example, if this is the fundamental mode of vibration of the string, which represents one particle, if I double its energy, I'm going to double its energy and see if we can find any difference. So look at that. When you double its energy, look at the mode of vibration. This now represents a different particle. And if you increase the energy, look at the mode of vibration. There you have a third mode of vibration of that string. And you can continue increasing the energy, and you see how the modes of vibration changes. Now, this kind of string is an open string. You can also have a closed string and see what happens when I increase the energy. Now, this is the fundamental frequency of the closed string. That's the fundamental string. If you increase the energy, what happens? What happens when I increase the energy? That is the second mode of vibration. This is a different particle altogether. So by changing the modes of vibration, remember, modes of vibration means energy of vibration. The energy of vibration here is double the energy of the fundamental that you have seen. What happens if I now increase the energy further? Well, the mode is now different. You have yet another particle. Let's increase the energy again. You have yet another particle, and again. You see how string theory basically explains the existence of all these fundamental particles. So, according to the present day belief, but not all physicists, the string theorists believe that everything in the universe is made up of these fundamental strings, and many different particles are created by the different modes of vibrations of these fundamental strings. Alright, let's move on. Now, while strings in string theory are one-dimensional, you see, the string theory is very strongly supported by beautiful mathematics. While the string that you saw are one-dimensional things, the universe that describes, or the universe that makes up these strings, when described mathematically, requires about 11 dimensions. Now, how many dimensions are we familiar with? You know that you got X direction, Y direction, Z direction. We got 3 spatial dimensions and 1 time dimensions. So we are 4-dimensional people. Now, can you figure out a universe which has 11 dimensions? But there are some string theories that talk about 28 dimensions. Now, the question is the universe multi-dimensional? We are only used to 4 dimensions. Can you think of a world where people like us are 11-dimensional, 12-dimensional? Now, what is the difference there? Now, let me see if I can explain that difference. If you are a one-dimensional person, and if you live on this rod, say, remember you are walking along the rod, you are a one-dimensional person. You cannot see me, because if you have to see me, you have to understand the meaning of left and right. A one-dimensional person do not understand. A one-dimensional person can only understand front and back. There is no left and right for a one-dimensional person. Once you have left and right, you are introducing 2 dimensions. And if you introduce down and up, then it's a 3 dimension. So you see, people like us understand back and front, left and right, down and up, 3 dimensions. And we also understand the dimension of time, don't we? So we are 4-dimensional person. Now, a person that is one-dimensional will only understand back and front. So if you are a one-dimensional person and walking on this, You cannot see me. Although I'm here, I'm holding you, you don't know me. You see that? That means if there is a person who is an 11-dimensional person, that person may be among us, we don't know. Well, that brings us a lot of possibilities to talk about. What is multi-dimensional actually means? Now, it can mean many things. Well, our life in this world now may be a 4-dimensional life, and there may be other forms of life which are multi-dimensional, 11-dimensional, 12-dimension, 28 dimensions. And maybe we migrate from one world to the other. When we finish here, we probably go into another world of 11 dimensions. Now, have you ever thought of, or have you ever heard of somebody saying, hey, I thought I saw my grandmother just this morning. Well, I don't want to frighten you with these things. But when you finish living in this world, you probably go into another world of much more dimensions. That's possible. I'm just putting out feelers for you. You see, the theories that describe the universe gives you endless promises to think about, dream about, and make your own theories. That is the beauty of theories like this. So, if string theory is to be a theory of quantum gravity, then the average size of string should be somewhere near the length scale of quantum gravity, which is 10 to the power of negative 35 meters. A trillionth of a trillionth of a trillionth of a meter. It is so small that we will never be able to see a string. So unfortunately, this means that strings are way too small for us to see. So as scientists, if you want to see something to believe, if you want to experiment with something to produce results, it is not going to happen with string theory. And this is the greatest objection raised by many people about string theory. That is, this is mathematical fantasy with many people. You see, it is a dream with many people. It is not real. So we still don't know what the fundamental theory behind the string theory is. And we still don't have a unified theory that unifies all the theories that explains the universe. That means we still don't know what the universe is made of. We still don't know the exact nature of the universe. Where did all this start? And where is all this going? Now, all these things are still mystery for us. So, from judging from the established relationship, it must be a very interesting and rich theory. You see, string theory is a very interesting mathematical theory. It's got some beautiful mathematics in it. And we would hope with time we will be able to resolve the problems that it has now, and we will be able to find a theory that will unify everything. So, did you appreciate the journey that we have been doing in the past 3 sections that I have taped so far? 3 parts of this lesson. The journey to explain the fundamental nature of the universe. Well, just like any science question, we haven't really found a real answer for it. But we have made a beginning, and scientists are still striving for it, and hope in the near future we will have an answer. Well, this is the end of this lesson, and this unit has one more lesson that we will talk about in a little while. Alright, I'll see you for that lesson later on.